Dr. Iain Walker, who is a scientist also at Lawrence Berkley National Laboratory. Iain's area of expertise are similarly in the area of retrofits, zero and low energy homes, heating, ventilation, moisture control, and also simulation of building modelling and commissioning buildings, something that we don't do enough of here in New Zealand, and also diagnosing problems. He's executive editor and a board member of the Home Energy magazine, and is on the task. He's a task group leader for building and duct systems at American Society of Testing Materials. He's on the National Standards Committee for IAQ at ASHRAE as well, and is the along with.
Move around, Matthew.
Ah, yes. I'm proud you went to 62.2, which will be a great bedtime reading for me later on today. I'm glad Iain mentioned it this morning, but he was quoted in an interview with Alison Bales a couple of years ago that we used to ventilate mostly for just odour and moisture control, basically when things start to smell bad. But now we're starting, we being educated and more mature markets, are starting to think about the actual health consequences and the health implications of airtightness and poor ventilation. So,
okay. So Max gave a really, really good general introduction. I'm going to dig down into a few of the issues that we have faced over the years, and hopefully some of the mistakes that we made you won't have to. I'll touch on some of those. And also, like Max, I'm going to ask some questions that it isn't exactly clear what the answer is, but maybe we'll have a little conversation this afternoon about it and so where we want to be. And so I'm going to talk about what is, we say build type ventilate, right, what does tight mean and what does right mean, I suppose are the questions everybody asks. So let's start out by talking a little bit about measuring leakage in homes. Can you put your hand up if you've ever measured the leakage of a home with a blower door? Has anybody ever done that? Some of you, a few of you? Because it's not particularly common, right? And in the US, it's a little more common, but not everywhere requires it. It's going to be much more popular. But before you embark on, say, a national program to decide if you're going to do that, one of the things you need to think about is, so we measure how leaky the house is. But what sort of a metric are we talking about here? The one that Max talked about a lot, the one that we use a lot in the US, and is quite popular around the world, is something called ACH50, or air changes at 50 pascals, where basically you put a big fan in the doorway, blow some air in a house, and you blow air in that house until you can get 50 pascals across the envelope, write down that airflow. But to convert that into air changes per hour, you have to divide by the house volume. And that's probably a pretty good metric if we're concerned about indoor air quality, because it's about diluting pollutants inside, and so it's the fraction of the volume that you care about. It's used, like I said, in many, many locations. There are other metrics which are thinking more about how big is that hole? If I had to put all the leaks, all the little cracks together into one place, how big would that hole be? Now, that's something that's sort of maybe a little more easy for people to visualize. If you're trying to think about how leaky is my house, how big are all the holes if they're stuck together. Different standards in different countries have picked different reference pressures for that. Some are at 4 pascals and some are at 10. It gives you a little bit of confusion, but you could pick one and go with it. And then there are other various normalizations. You could divide by floor area if you care about energy intensity calculations, like most energy codes do. If you're just concerned about construction quality, you might want to divide by the actual envelope area, which is a little harder to either measure or know. We usually know floor area pretty well, and the volume pretty well, and particularly if you have complex house shapes. If you have a nice, simple rectangular floor plan, it's relatively easy to get envelope area. If you have lots of bay windows or dormers or L-shaped or U-shaped or courtyard homes, it gets a little more complicated. And then the last one is, instead of saying how much area do I have in the area, you just look at the flow. At least a second at 50 pascals per envelope area. And the one you want to pick probably depends on what you're going to do with it. If you want to be more like the rest of the world, you might go with ACH50, but if you just want to be on construction point, you might want to pick something else. I'm relatively agnostic on this because I think the one you pick depends on what you want to do with it. Right? But all of these can be calculated from the one blower door test, by the way. This is a way of taking the results of that test and turning it into something else. If you want to do blower door testing, there's a whole alphabet soup here of organizations. I picked the ones that we work with, which is ASTM, the American Society of Testing Materials. There's ISO, which is the international one that used a lot in Europe. CGSB, Canada has to be its own thing, so they have their own standard. Those are all multi-point testing, where you test the envelope over a range of pressures. Then there is another oddity, ASTM 1827, which I don't think many people are using, but Max was heavily involved in its creation, which was we wanted to minimize the errors. Once we did the first step of looking at blower door testing, how to get the errors smaller, and we quickly realized if you have only a certain amount of time to take your measurements, if you concentrate your time at low pressures and high pressures and skip the ones in between, you can actually get a better test accuracy. And so that was a test method that we call the two-point test method. We only do high, you only do low, and you skip the ones in the middle. You could argue that you lose some of the diagnostic capabilities, and by that I mean, if you're at home with a blower door and you're slowly increasing the pressure difference or writing down the airflows, you can tell when strange things happen, like if a damper blows open, for example, inside a duct or something like that. You'll see it with a multi-point test, but you don't see it with a single point or the dual point test. And lastly, single point testing got to be really, really popular, but there was no actual uniform standardized way of doing it until we created a test method through an organization called RESNET, which talked about how do you test at a single point. And a lot of the details here are about things that we want tests to be repeatable. So if I test and then you test, we get the same number. Or if I come back a year later, we're going to do the test the same way. And so a lot of what these standards talk about is things like, what do I do when I prepare the building so that the next person might come along and test it does it the same way? So you have to talk about vent opening and flues from combustion appliances. What do you do if a house has a basement? You're going to close the door? You test. We better agree on that, right? Because otherwise you'll get different numbers and so on. So there's a whole bunch of issues about you better agree on what we want to do for building preparation. Multifamily is always going to be a little trickier because from an energy perspective, we probably only want the shell leakage of the outside walls. That's all we want. But for an individual unit, you probably want to know the total leakage of that unit because we don't, from an energy point of view, it might only be the outside wall. But if you're concerned about transporting odors, contaminants, and moisture from one apartment to another, you need to know how much they talk to each other by airflow, so you need to know the whole airflow leakage. And the last thing I want to talk about is, again, talking about errors and so on, which is that there's a complication in all of this that has to do with the relationship between the flow through a building envelope and the pressure difference across it. And the problem is that is not linear. If you double the pressure, you do not double the airflow. And so from an engineering perspective, when we think about uncertainties and so on, this gives us a lot of heartache. Right? And when we're testing at 50 pascals at very, very high pressures, we know a building is operating really down at something like 1 pascal or less most of the time across the leaks. That's a long way away from 50, and are those things the same? And so I have a little plot I want to show you that talks about this a little bit here, which is, we call this the extrapolation problem. We do our testing at 50 pascals, let's say, for the single point, but there's this relationship between the pressure and the flow that is different from house to house. And the little green lines there are showing different relationships with the pressure and flow for different homes. And if we extrapolate down to the 1 pascal that we care about, where a building actually operates, we can see the errors can get quite big. Now, whether you care about that depends on, are you just trying to make all houses tight, or are you trying to use that in an energy calculation? Those are two different things. If you want to infer some sort of energy use, you have to understand these uncertainties. And it sort of is one step removed from, we just want to test a home. Now we have to test and think about uncertainty, which makes people's heads explode. But we need to think about these things if we're going to specify test methods. And this is showing us the reason why we often like to test at 50 is because if it's windy when we test, and we're testing down here at 1 Pascal, you easily get a lot more than 1 Pascal variation due to wind blowing on a home when you're testing it, which is another source of error if you wanted to test at the low pressures that we think homes actually operate at. So what happens is there's a trade-off, right? We can test at 50 pascals and be very precise and always get the same number independent of whether or not it's windy, but unfortunately we tested at the lower pressure, we have this extrapolation error, or we can test at lower pressures but be more susceptible to wind. And at some point there's sort of a crossover between the two. So if you're thinking about what sort of tests we want to use as an industry and when we want to maybe give people advice about when to do multiple or single point testing, these are just the results of something like 6,000 blower door tests that looked at this effect. And you can see that the little X's there of this multi-point testing, and as the wind gets faster and faster, the errors go up. Whereas for the single point test, the errors are about the same. They're pretty much independent of how windy it is. And at something like 6 meters a second, the errors in the multi-point test get bigger than the errors in the single point testing. And so if you're thinking about a standardized way of doing things in your industry, you might want to do things like not just have one test, but allow both kinds of testing, but give people advice on when to use one or the other. So hopefully now you have an understanding a little bit about what the rest of the world has been doing in terms of air leakage testing and how we might optimize that so that you folks can have a good way of doing it in your industry. And now I want to talk a little bit about some of the things Max touched on, which is, okay, so I've measured how leaky my building is, how leaky is too leaky, or how leaky is not leaky enough. And in the US, we've kind of been there a little bit. We have these airtightness requirements that are in most counties in the country, but not all. And basically, we change how tight we think a house should be depending on the climate that you're in. Which means that here in New Zealand, maybe you have a different air leakage limit for different cities, for example, between the North and the South Island, because you have different climates. And here in the US, we allow homes to be a little leakier if they're in the South, where the climate is kind of mild and not elsewhere. And as Max pointed out, California always has to be special. So the country does this, but not California. We don't actually have a leakage limit. And as Max said, some of this has got to do with the fact that we have our very own energy code, right? We don't use the AIVC. We have relative amount of times. Typically new homes are about 5 air changes an hour at 50, which is not so different from this, except that, of course, California is in the climate zones where this says the recommendation is 3. So we're a little leaky. And we've been recently testing some high-performance homes in the state. By high performance, this is about 30% better than code from an energy perspective. So not necessarily a zero energy home, but a pretty good home. And they're down at target. They're targeting, the builders are shooting for something like 4 to 4.5 ACH50. That's what they use in their energy calculations. Well, they're actually achieving better than that. But that's what you want to have, right? If you set a limit, you have to beat it. And they're beating. So a high performance California home, that's where we're at. Right? And by high performance, I mean about 30% better than code. So a little further north of this country is this country, which has real weather. Right? It's actually quite cold. And they have much tighter restrictions, right? The Hot 2000 program, for example, which is for high performance homes, we're down at 1.5 ACH50, which is getting pretty tight. All those homes are going to have some balanced heat recovery system because these are homes in a harsh climate. And I picked out Vancouver because it has the mildest climate, basically, in Canada. And they have a number like 3.5 ACH50. That's a place where it snows, you know, for a couple of weeks of the year, but not the rest of the time. So maybe comparable to some climates you have in the south of New Zealand. Right. Other typical cities, if you look at their, you know, the amount of heating degree days they have, they're pretty cold. You need a tight home. But this isn't. These are not the tightest homes, right? Some of you probably heard of passive houses. Anybody? Yes, maybe no. Passive house is trying to very, very strictly limit all the heating loads, including that from air leakage, and they're going all the way down to 0.6. So there's a range here. Some of it's depending on climate. Some of it is depending on what it is you're trying to do. I mean, these passive houses are really probably never going to be normal construction. It's very unlikely that passive house will be what everybody builds. We might go to zero energy homes, and those homes in California that are getting 30% better than code are getting close to a net zero home, for example, if you put some PV on the roof. So there's a lot of variation here, but the point is you might want to have different numbers depending on where you are in the country. Max talked about the building tightness limit as a place that might be a way to transition from building leaky homes to building tight homes. And I wanted to give a little bit of an example here. This is based on calculations using the ASHRAE standard, standard 62.2, because what the ASHRAE standard says is based on the floor area of the building and the number of people in it, and we don't actually count people because people are hard to count, we say you take the number of bedrooms plus 1. So a 3-bedroom house has 4 people in it, nominally. You can calculate the required airflow rate. So the example of this is that horizontal black line. That's something close to ADC, about 40 liters a second. That's what that said. And if we look at homes of different envelope leakage, there's a calculation procedure in the standard that says, if you tell me how leaky the house is, and where it is, and the where it is this climate factor that I've got color-coded there, it will calculate an airflow rate. And those different colored lines are those airflow rates, and you can see as you get a leakier and leakier house, you get more and more airflow. And at some point, those natural infiltration numbers are the same as that number that's required. And effectively, that's when Max talks about the building tightness. Now, that's what we're talking about. At what tightness do you not need to add a fan anymore? And this shows that, again, there's some climate dependence, right? In a mild climate, you're going to need a leaky house. And that's a pretty leaky house all the way out to 12 AC 50. But this is what the building tightness limit does. It basically says, we'll calculate what the airflow rate is due to natural infiltration if you tell us where you are and how leaky the house is. So this was used a lot in years, although as Max says, we've gone away from this, particularly as our new homes are all now down here, and almost no climates is there any way you're going to have a substantial amount of infiltration contributing. But we still do allow you to allow for this extra little bit here. So you don't have to put in a 40 litre second fan if you take account of infiltration in the ASHRAE standard. So that sort of gives people a little bit of I guess I was going to say some leeway. We're finding though that most builders aren't taking advantage of this. They're not measuring the homes and taking advantage of the fact that they don't have to put in such a big fan. And they're doing this anyway, and I have a few slides later on what that might mean. It certainly is simpler, right? And if you're allergic to testing, and some builders in the US are definitely allergic to testing, you can just put the fan in. You have to measure the leakage, just put the fan in and go. So this works sort of okay in new construction if you're thinking of type of limits and so on. But what about when we're retrofitting homes? Can we realistically get down to these low levels?
Can I ask a question?
Yes,
I just want to talk about that graph a little more.
Yeah.
Are you saying that added fan ventilation is necessary up to sort of 10, 12 air changes per hour?
That's correct, yes, in a mild climate, for sure. It might be a very small fan, right? I mean, when we get all the way over here, the fan that you need is only a very small fan.
Yeah, but isn't 12 air changes per hour a very leaky home?
It is a very leaky home, yes. All those things are true. So if you have a leaky house, you won't have to put a fan in. If the climate factors which are changing effectively the temperatures and the winds that are driving the airflow through the building envelope, that's right. So it's basically an estimate of the infiltration that you get for a particular amount of envelope leakage, and offsetting that versus the total that you need, and you make up for that by installing a fan. So yeah, it does sound kind of crazy, right? It says, well, I still need a fan for 12 inches. Yes, you do. Of course, if we had set our requirement lower, then no, you would not. Right? What if we only required half that ventilation? If we said that was acceptable for indoor air quality, we set it at half, then you wouldn't need a fan in that leaky house. But if we were in Europe, and I had to take this point here at, say, 80 CFM or 40 liters a second, and bump it up to, say, 120 CFM or about 60 liters a second, then basically you'd always have to add a fan no matter how leaky the house was in order to get to that half a net change an hour that's required in Europe. So there is, for those higher standards, it's going to be almost impossible to get there with a leaky house. It will be leaky enough, in other words. But these are for mild climates. I picked these because we're in a mild climate here. If I was to add some of the northern tier climates we have in North America, say in Canada, so it gets much colder, of course, that's no longer true. You get more and more lines that are steeper and steeper here, and the requirement for a fan goes away at a lower air change rate.
Can you say which climate factor the North Island of New Zealand applies?
I can.
Corresponds with?
Yeah, it's roughly the green line there, 0.5, which is.
Can you repeat the question?
Oh, I'm sorry. So the question was on the North Island of New Zealand, which of these climate factors would apply? It's the number roughly like 0.5. The median one for the whole of the US is something like 0.5 to 0.55. So that includes some very mild climates too, not so mild climates, not weighted by population or anything. It's just looking at if you look at all the weather stations and so about 0.5 is for the. So let's talk a little bit about retrofits. Max mentioned this air leakage database that we have. Some of the homes in that database were homes that were measured before and after a retrofit. And so we pulled those out to look at how much tighter the homes are after they've been energy retrofitted. Some of this energy retrofitting was just insulation, some was also air sealing. So there's a big range of things that were done to the homes. But generally we find changes on the order of 20 to 35%, something like that, is what can be achieved. If you just focused on air tightening, you could almost certainly do better than this, because this includes homes that did not have a big focus on air tightening. So you could do better. Well, this sort of gives you an idea of, if you look at something like what we've got about 30,000 homes, which is a larger database to do some statistics on, these are the sort of savings we can get when we're retrofitting homes and think about reducing air leakage.
Could you just explain, because there's been a lot of graphs, so these
Yep.
lines, these two boxes for everything, what's the...
Sure, I'm sorry. So, personally, I actually don't like this way of displaying data, but it tries to capture a lot of things. So, the bar in the middle is what we call the median. That's the middle. The shaded areas are capturing plus or minus 25%. So, half of the homes are inside the shaded box. And the other half are captured basically by the limits. So, the spread is very big here, right? So the difference between different breakouts of homes, there's a lot of overlap because the spread is very big. It's very, very dependent on an individual home as to how much air tightening you can do and how it's successful. Depends on how it's constructed. Could you find the big holes, things like that. So yeah, I apologize for not describing these graphs better. I just want to wave my hands really and say, look, one is bigger than the other. But now you know. Does that make sense to everybody?
Yes.
Yeah, good.
Change my life.
Go ahead.
These air change rates are under the 50 pascal pressure, so
Correct, yes.
you divide them by 20 approximately to give you what you kind of get.
I was hoping you wouldn't, that nobody would ask that question.
Natural.
Yes, so this is the result of a blower door test where you deliberately pressurize to 50 pascal. This is not the ventilation rate of the home as it operates. Absolutely not. And you suggested the rule of thumb, which is to divide by max value. Yeah, maybe it's divided by 40 instead of divided by 20. That's again very squishy. So let's imagine that you have installed a ventilation system. Do you know if it's working? I know this because I've talked to a few of you today who've talked to me about, well, if I put this fan in the bathroom and the door is tight fitting and I close the door, do I still get the exhaust flow from the bathroom? Maybe, maybe not. It's going to depend on things like what type of fan have you got. There are two kinds. There are axial, which means when you look at it, you see fan blades spinning round and round, like you've normally seen the cartoon-style fan. And then there's something called a squirrel cage blower, which is a round thing like this, which looks like a squirrel would run around and around in. And they have completely different characteristics. The axial fans care a lot about things like airflow resistance and do you open and close the door. The squirrel cage one's not. So the answer to that question is yes, but maybe no. Did it matter? In the US, we've almost exclusively gone to the squirrel cage ones, by the way, primarily because we included noise restrictions. The ASHRAE standard, for example, says you can't have a noisy fan. That's not allowed. And the old axial fans turn out to be noisy. And so the market moved to squirrel cage blowers just so they could meet the noise requirements. Coincidentally, they are much better blowers in terms of how well they perform with an airflow resistance. And so that's sort of an incidental thing where we got better airflow performance because we wanted quiet fans. And I know from talking to some of you that that's not necessarily the case in the New Zealand market. The fans we have available are not all squirrel cage blowers. But maybe that will happen if you require them to be quiet also. But anyway, let's imagine you've installed a ventilation system. You want to make pretty sure that you're getting that airflow rate, particularly if you build a tight house. You are now completely dependent on that fan. There's no, or very little natural infiltration happening. There's no safety net for you. And you know, we're dealing with fear today, at least that's the subtext here, right? What to be afraid of, what not to be afraid of. So you'd really like to know what you installed. So I'm going to talk a little bit now about measuring stuff. So we actually have some standard measurement protocols. There's a standard put out by RESNET called Standard 380 that talks about all sorts of different ways you can measure the airflows of ventilation systems. And the airflow, the ways to do it depend on whether or not it's an inlet or an outlet, or do you actually have access to the duct to measure it? So if you were living in this home and you could access the ducts like you can here, you could maybe put something in line and then measure the airflow. That's pretty unusual in a home. Normally you can't look up and see the ducts. That's pretty rare. And if you ever finish this place, you won't be able to see those either. So there are various techniques for doing it. There are things like flow hoods and so on. Some things are easier to do. Outlet terminals have proven to be quite tricky to measure the airflow out of, because often the flow is not very uniform. And airflow devices over the years have been developed to work well with very uniform flow. That's how they are calibrated, it's how the manufacturer designed them, and now we're using them in a situation where that's not what the flow is expecting to see. And so we've developed, we being the airflow measurement research community over the last 20 years, so it's the royal we, not just me, we've developed various ways to measure outlet terminals, and the ones that we usually use is something like we call powered flow hood. For those of you who ever worked in commercial buildings, there's a whole industry making flow hoods. They're all passive, but and they work very well on very good diffusers, but not for small diffusers or for residential applications. And basically, the only way around that is to have some sort of what we call a powered flow, which is a flow with a fan built into it and a flow meter that makes it insensitive to incoming airflow. And there's a few of these available in the market. Or for amusement, you can build your own with cardboard boxes and flex ducts, which looks incredibly non-professional, but it's very precise. Speaking of which, you can. I'm not a physicist like Max, but I am an engineer. So I like what works. And I like this idea of actually measuring the flow and with a stopwatch measuring time. If you want liters per second, measure liters, measure the time. All these other airflow devices that have ever been made are not measuring volume and time, which is what we want. So why not inflate a plastic bag, right? And in Canada, they knew about this years ago. It's very simple, easy to do. It's hard to it's hard to justify in terms of if you're a contractor going out and doing something, you look like you really know what you're doing. There's nothing with a logo on it or what have you. But this was guidance put out many, many years ago by CMHC up in Canada. They talked about, depending on the size of the bag and the amount of time, how much airflow is that. It's a very fundamental measurement. It's vaguely amusing, so I've got a little film here to show you. I apologize for the resolution. This is from the 90s, so it's a long, long time ago. But basically, you have a bag and you make a little frame, and you time how long it takes to inflate. And it turns out, it looks really like kind of a joke, and we can laugh at this, but it turns out it really works well. It's repeatable, and as long as you have access to the registers, it's a great way to do it. Inlet terminals are a bunch easier because you have a uniform flow entering the airflow device. There's a whole bunch of devices out there that will do this for you. You can even build your own if you can know the area of a box and measure the pressure difference. Relatively easy. These things can be done passively. There's all sorts of manufacturers. I'm not advocating you buy a TSI Allen or Hood. It's just this is what I had a picture of. They come in different colors and sizes and so on. They have some limitations. Some of them won't go down low enough for low flows, right? These big ones in particular won't. They make smaller versions, but they're still not very good at low flow, unfortunately. And
that one you showed on the previous slide,
yeah.
the bottom like this.
And lastly, the thing I mentioned, if you can actually look up and see the metal ducts like we can in this room, and you have a long enough section of straight duct, you can use what I would call traditional engineering methods, which is to measure the velocity pressures and try and map the velocity flow from there. It's a bit tricky and unwieldy, but it can be done. What we are seeing, though, is in some ventilation devices, particularly heat recovery ventilators, manufacturers are starting to build these in, which is going to make our lives much, much easier. If there's a flow station built into your ventilation system, maybe all you need is a pressure gauge as a diagnostic tool. That makes it way, way easier. We'll wish this happened more, but it's coming, I think. Max terminals, I'm going to skip a bunch of these because I want to get to how tight is tight enough. Again, Max touched on some of this. In new homes, if you get to about 38650, which is the IECC requirement for sort of the climates you have in New Zealand, that captures 80% of things. You could go tighter, and for high performance homes, fine. Go as tight as you want. For voluntary programs, fine. If you want to be like the leading edge builder, fine. But if we're talking about generally from a building code, what's the worst house we will let you build in New Zealand, maybe a number like 3 to 5 is where you want to end up. I don't think you want to be much looser than 5, because you end up with bigger energy penalties and so on, and also you don't control the airflow so much anymore. They get to be high in the winter and low in the summer, and that can cause air quality problems. So the 3 to 5 range is probably reasonable, and you might want to do that tighter ones in the colder climates. You probably don't need to go to these super tight things. In terms of retrofitting, if you have a relatively modern house, maybe you can get to that 5 ACH 50. More than likely, though, you're going to aim for something like a 50% reduction. Getting to more than 50% reduction is super, super hard. I've tried it. It can take, if you have weeks available, sure. But in a practical sense, it's going to be super hard to get to more than half the leakage reduction in existing homes, which is too bad, but that's just been our experience. So I advise you to not require people to reach new home levels of tightness when they're doing retrofits in existing homes, because it'd be a very frustrating experience and people will stop doing it. So we've basically given people a break for that. So how much ventilation? Of course I'm going to throw ASHRAE 62.2 as I'm the incoming chair of it, but it's not the only ventilation standard in the world. There are others you could pick. In Canada and Europe, they tend to go room by room for ventilation requirements. 62.2 is the whole house. Different countries have slightly different tolerances for ventilation, as Max said. A lot of this scales with things like how big are your homes. Our homes are relatively big in the US. So in terms of air changes an hour, we're happier with a smaller number. But anyway, 62.2, it's about 0.3 air changes an hour, but it varies depending on how big the floor area is, and number of people is really number of bedrooms. But that's just the whole house thing, and I wanted to talk a little bit about some of the other things, like if moisture is your concern, and as what I've learned in the last few days is, yes it is, you definitely want to be exhausting from bathrooms and kitchens. And these are the numbers that we have in 62.2. We've done some field studies. These seem to be reasonable. This isn't a continuous flow, right? This is something where you have a switch on the wall, you walk in the bathroom and you turn it on. Or in the kitchen, we're talking about arranging something over the cooktop with a switch that you turn. Does not have to run all the time. The standard does have lower numbers if you want to operate something all the time, but almost no homes are built that way. They're almost always built with these devices inside. And it's really, really important when you're ventilating these things that it all goes to outside, that it doesn't go into the attic, for example. Or, particularly for the kitchen, don't use recirculating ratios because they don't do anything. They genuinely, you can imagine, of course they can't get rid of the moisture because they don't throw it away. They might filter out some of the particles that we worry about for indoor air quality, but only while the filter lasts. And we're finding out that people don't reliably change their filters. It doesn't get rid of the gaseous contaminants such as nitrous oxides, running out of gas and so on. So don't put in recirculating rangers, they've got to vent outside. However, this is based on typical homes, giving you a minimum point. You can always do better, right? And then you get into your own personal trade-off between more flow, which is generally going to be more energy, but it's going to dilute the indoor contaminants more. So there's a trade-off between air quality and energy. This is just talking about a minimum, and almost all the ventilation codes in the world talk about a minimum requirement. What's the least amount of air we're going to let you move and say it's acceptable indoor air quality? And when it's acceptable, it's not perfect, right? It means that some of the time, if you do this, things are still not going to be good, right? For example, if you have smokers in the house, is this level of airflow going to guarantee good air quality? No, it is not. If you're concerned about radon, and I know it's not a particularly New Zealand thing, but other people are concerned about radon, you probably have to have a radar control system as well as this. If you have strange hobbies, maybe you have 20 tropical fish tanks in your home and have a huge moisture source. Or what if you like playing with electronics and you're soldering all the time, creating all sorts of crazy vapors? This is not accounting for that. This is just a baseline minimum. You can always do better. But this is so. But from a builder's perspective or a contractor's perspective, you can deal with all those complications anyway, right? And it's not fair to ask builders to do so. So this is where we are. There are some other things you could do though that would, aside from moving a lot of air around, which is what we've sort of focused on today, is what if you used low-emitting materials that emitted, say, less formaldehyde? Do you have such regulation in this country? Yes or no? Does anybody? Do you think no? That would be good, right? We've got it in California now. We're trying to go national in the US with this. This is talking about, often this is materials like compressed wood products and some plasticizers and so on. And the key one is formaldehyde that we worry about the most because we know that it's a known carcinogen and it appears at concentrations of concern in homes. But there are other VOCs too. We talk mostly about formaldehyde though. If you can put in low emitting materials, why not? Right? That would always be a good thing. There are other odd things like cleaning products that have that are based on things like oranges. You've probably all seen these, right? The limonene in there reacts with various things to create particles of a size that we know are a problem to breathe in. And so I love a clean house, but there's some cleaning products that might not be awesome. And it's very frustrating because we like to use natural products, right, in our home, but sometimes that's not always great. The caveat there does depend on things like is there ozone in the air and some other things going on, but there are definitely issues with cleaning products and so on. If you burn a lot of candles, that's not a good idea. You know what, if you like the light, do it. Just know that you're putting a lot of particles in there that might not be good for you. Cooking, I said, let's just put in a great range and always run it. That turns out doesn't always happen. People don't always turn it on. I'll talk a little bit more arrangements in a couple of minutes. And if you can deal with things like moisture by having exhaust fans in rooms where it's generated, and things like having good drainage. Site drainage is an incredibly strong impact on the moisture in your house. I personally have done this in my old house out in crawl spaces. Once I got the crawl space sealed off from the house and drained it properly, all my moisture problems went away. And I know that you do a lot of crawl space homes in New Zealand. Controlling the moisture in the crawl space is really important. It's site drainage and just covering up the dirt. Put 6 mil poly down over the dirt is a great moisture control strategy that is almost free. Right? That's a DIY thing. That's almost free, but it can really make a big difference. And then there's things like carpets and the materials where there are lists out there of products that say that they have that are tested, that have low emissions. It's a great idea to put those in. And there's all sorts of resources for this. I'm not going to go into too much detail. However, I do want to say that if you're going to go with this route of let's minimize what we're bringing in the house, prioritize the things with the big surface areas and so on, direct plastic corrosion. They're going to matter the most. The big question is, does it actually work? And I'm going to say, yes, probably. So we've actually done some studies in homes where we looked at homes with low emitting materials, which are the red dots in these figures, and compared to the black dots. And basically what we're looking at is how much formaldehyde is in the house versus the air exchange rate. And not surprisingly, as we ventilate more, the concentration goes down, which is a big relief for those of us who have long advocated controlling concentrations by ventilating. Right? It seems like it did work out after all. But we see that something like, I apologize for the fact that this is 24 and that says 42. Right, well, the thing with VOCs is their emission rate is incredibly strongly dependent on temperature. And just during the day in your home, the small daily temperature swings will change the emission rates by factors of 5 at least. And you should know that the hotter it is in your home, the more formaldehyde you're releasing. So in fact, the fact that you don't heat your homes is a great formaldehyde control. But anyway, the point is, we can actually go out and measure these changes in homes. So it really does work to pick those low emitting materials. It's not just marketing. It really actually can have an impact on the concentration of formaldehyde in your home. Cooking is always, who loves to cook? Anybody? I do. Most of you want to cook on gas, right? I'm assuming, but maybe electric. The problem with cooking is it's the single biggest source of things like CO2 and water vapor in the home, also oxides of nitrogen, formaldehyde, ultrafine particles, you name it. And unfortunately, all ways of combusting do this, but so do hot electric elements. When you actually include some food, you get even more stuff, right? And I understand this is going to be a trade-off. I mean, who doesn't like the smell of a lovely dinner being cooked? I mean, it's great, right? But there's a trade-off here between getting enough of that we get our juices flowing, and dinner's nearly ready and it's wonderful, and are we actually breathing in a lot of really, really bad pollutants? The solution really is range hoods. The question is, how well do they work, right? We can vent them outside, but if they don't work very well, are we doing any good? So we recently did a bunch of lab testing. We bought a bunch of range hoods of all sorts of different costs. And what happens if you tested a very controlled conditions? This is not anybody's kitchen. This is my colleague Woody in our lab kitchen, burning beans. What happens? They all of a sudden, unsurprisingly, they're not. So what we're looking at here is, this is the flow through the range hood. Now there's not the whole household, it's the flow through the range hood. And on the vertical axis, we have a thing called capture efficiency. That's a measure of the pollutants got created off the cooktop, what were captured by the range hood and got thrown outside. So we want a big number. 100% means no pollutants in your home. We nearly got 100% in some ways. They're pretty good. But you can see there's a big performance range. From about at low flows, maybe only 20% of the pollutants are captured, and the rest are not. So there's a big performance range here. And cooking on the front burner, which is where you want to be, right, because it's the one you have access to in season, that's always going to be the worst, unfortunately. And this is a simple geometry, right? It's how far from the wall the range. You can just mentally think about why that happens. So the results are all over the place. What you'd like to be able to do as a homeowner or a builder or a contractor or an IAQ expert is say, oh, let's buy the good one. But you can go, you double check on this. If you check on the packaging on your range, they don't say which this information is not reported. So we went into people's homes and did very, very similar experiments. And my goodness, the stuff is all over. Ignore the bit on the top, right? Just forget about that. So these are all individual homes. We tested back burners, front burners, combined them. The key thing is that the answers are all over the place. That is the answer. Is that there isn't an answer, right? The performance is very, very variable. And just to be fair, I highlighted which house was my house. It's sort of in the middle of performance there. It's not awesome. It's not terrible. But this meant that just specifying that you have a range hood is probably not enough, right? We need a way to say, this is a good range hood, this is not such a good range hood. So we recently developed a test method using all sorts of very careful calibrations and so on, and that's now an ASTM standard that's about to be adopted, and we're actually going to have ratings for range hood capture. Can't have that yet, they're coming. And once that is successful and all the manufacturers are doing it, that's something you can then specify, for example, in your building place. But I have a few quick recommendations, in lieu of saying buy one with a high capture efficiency, because you can't actually do that yet, but you will be able to do soon, it better be vented to outside. If it's not vented out to outside, stop. It's broken. You'd like to have it that covers all the burners, so when you're looking down, it actually covers all the burners, and probably something like more than 100 liters per second capacity to get the high capture. You want it to be quiet, and that means if you're installing it, that means short, big ducts, so low resistance ducting is really important. But if you don't turn it on, it won't work. So we can try and, there's efforts underway to do more automation, where they will detect if cooking is happening. It turns out it's quite tricky to detect if cooking is happening, not as easy as you might think. In the meanwhile, just tell all your friends to do it. Every building site you're on, tell everybody, put big stickers on the wall, whatever it is. So that's ranges. So another thing is about particles. Particles are sort of the most important thing from the perspective of health in a home. Once we've done moisture, go to particles is next. And there's some interesting oddities about related to typing and stuff. It turns out that if you change the leakage of a home and measure how much particles penetrate, tighter envelopes have lower penetration. You're actually having less of the outdoor particles come in your house with a tighter envelope. So putting aside all these other things about energy and so on, a tight envelope is actually pretty good. Now, this is for submicron particles. We'd like to test larger ones. But basically, the good news here is if you build tighter, you can stop the outdoor particles coming in. The flip side of this is that don't ventilate with open windows, because then all the particles come in and you're at zero. And not a good thing, but this is sort of more good news for people who want to tighten envelopes, is the envelopes themselves can filter out some of the things that we don't like. We recently did a study looking at all kinds of different ways of filtering, because maybe dilution is not always the right answer, right? Maybe some things like particles in particular, we can filter them out. Right? So unfortunately, the results here look a bit like for the range hood, right? So here we have, along here we have, each one of these is a different filtration system, different way of filtering, and the vertical thing is telling us how much filtering they did and what the final indoor concentrations were. In this case, a low number is good. Low number means zero particles. And once again, just like with the range hoods, unfortunately, not all systems are created the same. These systems did great, these not so much. And the key thing to doing a great job of particle control is that you need to have something which is filtering all the time. Now, all the time doesn't mean all the time. All the time would be a low flow, say 100 liters a second through a filter continuously. But, and in the US we have central forced air systems that can maybe operate on a timer or so. But you really need to be, for a filtration to be effective, it needs to be all the time. And this is more of the same. So you could skip the central forced air system because you don't do that. But if you did, you could put a MERV 13 filter in. If you're going to do supply air though, remember I said that the envelope is a good filter. If you want your supply air system to be doing as well as a good tight envelope, you need a MERV 13 filter in there. Who knows what MERV is? Is that something people hear from it? So MERV is a minimum particle. It's a filtration rating for particles. Higher is better. MERV 13 is one that's going to get most of the particles that we're concerned about for health. It's just a rating system for particle filters. We talked a little bit about commissioning, and I only have a few minutes left, so I want to, I think we touched on all these points about this. The question is, how common are faults in places where we commonly install ventilation systems? Well, in Canada, they love HRVs, but they found all of these terrible problems. Some weren't operating, some were out of balance and so on, because they were not maintained. And when we put in complex systems like this, maintenance becomes an issue. So, much as you might like an HRV, particularly in a colder climate, you still want it to be an HRV a year later, 5 years later. So somehow the people who are going to be living with that device have to know about it. That has proven to be very difficult to do. If you look at some homes we measured recently in California, we have these target exhaust flow rates, and most of the time we weren't meeting them. Now, this is old data, we're doing better than that. But this is a concern, right? This is why we talked earlier about maybe we should measure these things. Again, looking at HRVs and ERVs, we have a lot of things, problems with failed connections, variable speeds and so on. there's a whole world of pain out there that's coming your way once you start putting mechanical ventilation systems in houses, particularly for complex ones. And what I'm telling you now is be aware of this. And the way to get around it is you really need to be measuring the airflows. And somehow, even if you did that and you installed a perfect system, you measured all the flows, it was excellent, all the connections were correct. All this sort of nonsense happens where this is test results from a study done in Florida. Again, this is mostly for supply systems. There's an outdoor air inlet, and they all get plugged up, and once they get plugged up, they don't work anymore. And no homeowner has this on their schedule of things to do. So a big caveat about ventilating homes, if that's where New Zealand's going to go, is people have to understand what that means. By people, I mean the people who live in homes. Once you as a contractor or builder designer are long gone, this is what's going to happen down the road. And I've just got a couple more slides here. I do want to give you hope though, right? So this is a characteristic of supply systems and HRVs. It's often goes through the air inlets. What if you just put a simple exhaust fan in, which by the way, is by far the most likely way people comply in the US. A simple exhaust system, engineers might not like them because they're simple, but you know what? The little black dot there was the calculated airflow they needed to meet the ASTM standard. And the bar is for each house how much flow they had. And almost all the time, they're doing just fine. And on average, they're about 40% higher than the minimum requirement. There's a couple of homes that didn't quite make it. But that's going to happen, right? But these exhaust systems seem to be working fine. Because they don't have that complication. They don't have an outdoor area that plugs up. And because we're running out of time, I want to skip to one last topic, which is a thing we're calling smart ventilation. Max handed out a bit to talk about this. What we're going to do is do a better way of controlling ventilation systems. And what we're going to do is ventilate more when it's more favorable to us, or less when it's so that means that when it's colder outside, you'll ventilate less. And you'll make up for that by ventilating more at some other time. And we're basically sort of time-shifting ventilation. We'll also do things like, we'll measure when other fans like the bathroom exhaust, the kitchen exhaust are running, and include those airflows in our calculations. And these are the sort of savings you can get. It's something like 40% of the energy savings you can get with a smarter ventilation system, which is not too bad, considering how they're relatively simple. And the ASTM standard actually has all the calculations in it that you need to do that. So this is in theory. The question is, does it work? So these are a lot of dots. Each dot is an hour of a house where we had a system that's controlled and not controlled. The blue dots, or the blue triangles, sorry, were under the smart ventilation control case. And it's almost impossible to see this, but if you average these things, indeed the blue data is below the dots, and almost exactly lined up with our theoretical savings. So we've actually done this at homes and found out that it truly, truly works. We talked about this stuff. I've got one more thing I think to talk about, which is California. We're in the middle of doing a study where we're measuring indoor air quality in about 70 homes. But one of the things we did first was we asked people, this is getting back to, do people know what a ventilation system is? And if in New Zealand you're about to start installing these things, this is going to be one of the things you must deal with. We did a phone survey, an online survey of about 3,000 people, and something like 3/4 of people said, oh yeah, I know what my ventilation system is, it's okay. But then in the homes that we actually included in our field study, where people were now a little bit more like, oh, you're actually going to come to my house and test it? We're not quite so sure, right? So the data on the right is the people who knew they were going to get tested. They became a little less confident about it. But at least half of them were like, oh yeah, know what the ventilation system is, it's all great. Some of them are like, not so sure. But you know what? Out of the homes that we studied, only one home had the system turned on. So those half the people who said, yeah, I know all about it, they actually didn't. And the story here is that people don't detect indoor air quality particularly well. And there's some caveats for you if you're going to start installing mechanical ventilation systems. These homes have a switch on the wall. It was an unlabeled switch, which is not supposed to be, it's supposed to have a label. It was unlabeled because they had a mystery switch in their house. And when they flipped it, the lights did not turn on and off. Right? No, they were like, what is it? And so they ignored it. But it was the switch that turned the ventilation system on and off. So if you're going to put the mechanical ventilation in, if you're going to let people have a switch, if you're going to let the occupants do something with it, it better have big labels on it, happy face. things like that. You know, the skull and crossbones beside one. And whatever you're going to do, either that or you make it a life safety thing, or maybe you don't have the switch and you make it like we have done, for example, with carbon monoxide detectors in the US, where it's hardwired. There's no switch, not even a battery. It is just connected to the electrical system of the house. So I'm going to just finish there, I think, on that thought about this is just to make you guys aware of some of the issues we've run into, so you can be pre-informed when you go down this path about some of the key stuff. And this last topic of, do people understand ventilation? Do they know when things are working? Probably not. Does it matter? Yes, it does. And so you should think about these things when you start specifying, maybe in your building codes, or just in your own personal practice about, if I'm going to put ventilation systems in a house, what am I going to do to make sure that system, first of all, is still functioning 5 years from now? Which we talked about. Second of all, when I installed it, did it work? Did I actually commission it? Because you better commission it. And thirdly, after I walk away, do the people in the house know what to do? And particularly if you put a switch in, then let them switch it on and off. But this is the land of the free, where we're not allowed to say, you must have it turned on, right? You know, for the individual freedom to decide. And boy, do they have the individual freedom to decide. Anyway, I'll stop talking there and take some questions.
Have I got a couple of burning questions out there?
Ian, thanks for a great presentation on a wide range of things. I just had a question on the recirculating hood, because I'm particularly interested in that subject, and I've been involved in several passive houses. And of course, we don't want to put the air outside because we don't want to lose the energy that comes from the heat source.
Yeah.
So, I have been specifying recirculating hoods with carbon filtration and additional performance on the main filtration set for the oil atomized oils and things.
Yes.
Do you have any thoughts to add to that?
Yes, I do. So I've had this exact conversation with the passive house people in the US and in Europe also. And what we're finding is that more and more we are seeing kitchen exhausts and passive homes. And I understand the reluctance. That's heat you're throwing away, right? I mean, the California context, our problem is actually overheating in passive homes. So it's a little more acceptable there to be venting straight to outside. But in Northern Europe, they want to keep that heat in. The filtration is a good question. We recently have just finished some experiments with a recirculating hood looking at that filtration capability. And so long as the filters are new and fresh and change regularly, you can certainly filter out the particles with a particle filter. You can use activated carbon to do some of the chemical cleaning of the air. But again, my concern is you're really depending on the person in the home to become the indoor air quality expert and maintain those things, right? And lastly, I think you know the next point I'm going to make. It really does not do very much for moisture control, right? I think the moisture control is the hardest one for you to deal with if somebody wants to do a recirculation in a passive house. Is to do with the moisture problem. And I understand using so we can increase the whole house ventilation doing that. If you have a boost switch on the wall or integrated, right, where you maybe double the ventilation. That certainly helps for sure.
Just got one time for just one more.
Thank you. What about fire safety with high airtight houses and range of exhaust and potential fireplaces in there? Is there any research into that?
So you're talking about fireplaces elsewhere in the house,
Yes.
in a tight house, and you turn on a big exhaust. Yeah, don't do that.
Yes,
Right,
fair
so
enough.
let me be slightly more helpful than that. If you're in a passive house, having an open fireplace is probably not a great idea when you're at that level of airtight. Simply to get enough combustion air for the open fireplace. So what we're seeing in new construction, and there's quite a lot of legislation on it. Open fireplaces are basically not allowed in many places now. You have to have what we call sealed combustion unit, where the combustion air is taken from outside, and there might be some nice glass doors so you can see the flames, but you can't touch them. And the air is not coming from the house into the fire and up the flue. The combustion air is coming from outside, so you're basically isolating that fireplace from the rest of the house, and that's what we see in tighter homes.
I'm aware that a few people probably need to get going, but I have a bunch of questions. I'm sure some people do. You guys will be around for, we're going to keep you here anyway for another hour, so
Yes, we'll be around.
So please do feel free to enjoy a drink outside, ask more questions, talk to each other. Please join me in thanking both Max and Andy. Fantastic for me. I think what I was thinking is, pardon the pun, but it's a breath of fresh air, knowing that knowing that there are people saying what I think a lot of us are thinking, and that there has been that experience that these guys have been through and others around the world have been through. So this, I hope, is the start of lots of conversations of figuring out how we can get to some of this level of detail in a short space of time, so we don't have to go through a 20-year painful process of learning the same mistakes that have been learned. So thank you very, very much, guys. Please enjoy a drink. There might be some more food out there, I'm not sure. And feel free to stick around and ask some more questions. Thank you.